Nima, everybody today has heard the concept of the quantum, and we know that there's some tremendous developments happening in the field. So I really want to understand this, but let's start with understanding what is the quantum itself. How can we understand quantum theory?
Well, in the late 1800s, we had two basic kinds of phenomenon that we'd seen in nature. Things like light and sound waves and other excitations of different media were described by waves, but things like billiard balls and well, they didn't have cars, but if they had cars and other things were described as particles. Having these two different kinds of descriptions for phenomenon in nature started leading to some confusions. For example, when people described light as waves, and then they tried to figure out something very, very simple, like how much energy comes out of an oven, for example. And they applied the usual laws of classical physics. They got nonsensical answers, like an infinite amount of energy comes out of an oven. So there were paradoxes associated with the wave-like on the one hand and particle-like on the other hand description of the various phenomena that we saw in nature. And what people realized in the early part of the 20th century was that these two different things that were being described by classical physics, wave-like property on one hand and particle-like properties on the other, were in the end of the day all actually describing particles, but particles that don't move according to the laws of classical mechanics, but move instead according to the laws of quantum mechanics, which are very, very different than the classical laws that govern particles. For example, there was the famous uncertainty principle that said that while in the world of classical physics we associate the movement of a particle through space and time by specifying its position and its velocity at any given point, that we can't in fact specify the position and the velocity to infinite accuracy, and that if we know the position very well, we don't know the velocity very well, and vice versa. And all of this happened in conjunction with the realization that there's a new fundamental constant of nature, Planck's constant, which determined when classical approximations to the real underlying quantum physics was good, and when that classical approximation broke down. I should also say, I mean, there were many other paradoxes of this sort. The one that I mentioned about the infinite energy in an oven was the one that led Planck himself to the first realization that there was something wrong, and that the classical rules governing light had to be modified. The specific way it had to be modified was rather simple, by the way. Classically, we might imagine having a light of some given frequency. And we can make the power or the intensity or the amount of energy carried in that light beam as small as we want. And Planck realized that he could make sense of these difficulties with the infinite amount of energy coming out of an oven by positing instead that for a given wavelength of light or a given frequency of light, there was a certain minimum amount of energy that was compatible with that frequency.
And this is the discrete pieces.
And this is in the end the discrete piece, the quantum of quantum physics as it entered Planck's vocabulary was indeed to tell us that for a given frequency there was just an absolute minimum amount of energy that light could have, and it couldn't go any smaller than.
So energy comes in pieces,
so
in
that,
particles.
So that the energy in light indeed comes in discrete packets. Now Planck himself, while opening the door to this revolutionary concept, could never himself believe or buy all of its consequences. So in fact, it took Einstein to really make the leap and say that Planck's discovery meant that light came in little parcels, light came in particles, photons, and that at a given frequency there was a minimum energy photon whose energy was given by Planck's constant times its frequency, and that description of light made a number of correct predictions.
Now, today, we know that from this, there's a large number of observations which we know to be true, but which seem counterintuitive to our normal macroscopic lives. Particles entangled, tunneling effects where things seem to jump from one place to the other. And this seems to be impossible, but it is real.
It is absolutely real, and one of the unfortunate things about the way sometimes quantum mechanics is described is that there's an awful lot of mysticism associated with it, and uncertainty means that everything that we can't be sure of anything, and maybe consciousness has something to do with the way the world is, and there's an awful lot of nonsense said about quantum mechanics, whereas in fact quantum mechanics is responsible for the absolute stability of everything, we're made of atoms, for example.
Because the electrons can't occupy the same position.
Right. I mean, there was this old classical picture that an atom was like a little solar system with an electron orbiting around, with electrons orbiting around the nucleus. And there were a variety of problems with that picture. One of them was that you would think that the electrons would quickly lose energy and spiral into the nucleus, and atoms would be completely unstable. Right. And another one, a related one, is that even if you ignored that problem, you could imagine lots of different solar systems with lots of different distances, and why were all the atoms identical? Why is everything made out of the same stuff? And both of these mysteries were solved by quantum mechanics with the realization that it was impossible for the electron to fall into the nucleus, because if it did, you would know both where it was and how quickly it was moving at the same time, and the uncertainty principle tells you that that's not possible.
So the uncertainty principle actually creates stability and absolute confidence.
Exactly.
In the modern world.
Exactly. The uncertainty principle, far from introducing all kinds of fuzzy garbage, actually allows things to be stable and is responsible for all the gross properties of matter that we see in the world.
Okay, let's fast forward to today and tell me about these serious problems in quantum mechanics, and what are some of the potential areas of excitement and possible solution?
Well, in many ways, we have theoretical crises today that, in some ways, harken back to the sorts of problems that we had in the late 1890s that led Planck, for example, to introduce quantum mechanics to begin with. And it all has to do with the fact that in our understanding of quantum mechanics, and also putting quantum mechanics together with special relativity, actually putting these two things together forced us to introduce antiparticles, which are antimatter partners to ordinary particles. And the two of these things together give rise to this interesting fact that the vacuum, what we like to think of as just emptiness, is not really empty, and is a very, very rich place with all kinds of interesting dynamics. So that's something that's forced on us by both quantum mechanics and special relativity. And more or less, all of our problems have to do with those quantum fluctuations of particles and antiparticles popping in and out of existence out of the vacuum, as allowed by the uncertainty principle. Making sense of those fluctuations of the vacuum gives rise to a variety of real crises in our understanding of physics today. Two of them have to do with ultimately the question of why it is that we have a universe with such incredibly different and disparate and interesting length scales where interesting physical phenomenon happen. The tiniest distances that we've explored at our very highest energy accelerators is something like 10 to the minus 16 centimeters. That's around 100 times smaller than the size of a proton. The largest distances that we've explored are something like 10 to the plus 28 centimeters. That's around the observable size of the universe. And theoretically, in our mind's eye, we can take all the laws of physics that we know quantum mechanics, special relativity, and its generalization to describe gravity, general relativity. And using those, we can imagine extrapolating to very, very short distances, around 10 to the minus 33 centimeters, called the Planck length. So there are these huge, very, very disparate, interesting length scales, apparently, in the universe. That's a very salient fact about the universe, that there are incredibly different length scales. And yet, quantum mechanics, and indeed these quantum fluctuations of the vacuum, seem to be very much at odds with that very basic fact about the universe. For instance, quantum fluctuations of the vacuum have some energy. And Einstein told us that any energy gravitates. Any energy gives rise to some curvature of space and time. So if we take these quantum fluctuations in the vacuum and we just estimate the amount of energy that they carry and figure out what that would do to the universe, we get a completely nonsensical answer. That if you just do a back-of-the-envelope estimate, you would conclude that the universe is, for example, doubling in size, accelerating very, very rapidly, doubling in size, and the doubling time would be every Planck time. That Planck time is around 10 to the minus 43 seconds. Okay, so if you took a theorist and locked them up in a room and asked them to say, please, here is the universe, here are the laws as we know them, please give a prediction for what you think the universe looks like, they would not remotely predict the universe that we see, because the energy in the vacuum would be just grossly larger than what we apparently observe it to be. Okay, so that's one of the crises that we have.
And you've talked about that maybe we're missing something big.
Right. So I think the problems with these, with taming these quantum fluctuations of the vacuum don't appear to be a little technical problem or something, or a disagreement between theory and experiment in the 6th decimal place of some calculation. They are problems of, roughly 120 orders of magnitude. Or there is an analogous problem with for trying to understand the question why gravity is so weak. There too, the fluctuations of the vacuum want to make all the particles that we know and love much, much, much heavier. And if they were much, much, much heavier, then gravity would be a lot stronger because everything would be a lot heavier. And then you and I would be black holes. It would be a very unpleasant universe. So those are two questions that are directly tied to the quantum fluctuations of the vacuum that seem to want to drag things to as high an energy, as short a distance as possible. And one of the problems has to do with why the universe isn't accelerating every 10 to the minus, doubling in size every 10 to the minus 43 seconds. That's called the cosmological constant problem. The other problem of why we aren't all black holes is called the hierarchy problem. And they're each sort of very large, numerically very large problems. The amount by which the estimate and the answer is off is something like 120 orders of magnitude for the first one, 30 orders of magnitude for the second one. And so we think there's got to be some very big new principles missing that allow us to figure out why the answers are in fact what they are.